So I decided to do one more example of graph translation just to, again, give you more practice thinking about moving from one type of graph to another. And we're starting with position, and we're going to try and get all the way to acceleration from there. So we're going to go in order. You actually might eventually find it easier to look at a position graph and make a rough sketch of acceleration, but we're going to go in order from left to right. So I tried to make like a bit of a crazy graph. This is a curved line. That's a straight line, that's a straight line, and then that's obviously a curved line. And so this is like a little complicated, but we use our same concepts. So the first concept is the slope of the position graph tells you the value of velocity. And so this is the hardest part to decode. This line starts very steep in the positive direction. So I can maybe say, I'm going to start my velocity way up there and move on from there. Because what happens is this line gets less and less steep, and so the velocity needs to decrease. Specifically, if I continue my story, by the time I get to A and into B, the line is flat. So I can say that line A, with pretty good confidence, is going to start anywhere up high, and it's going to end flat. And so that's my first translation, is to take this curved position line and say, well, it goes from a very positive slope to essentially a slope of 0. And so I can do large positive value down to 0. B is meant to be kind of easy. It's a flat line on a position graph, which means the position isn't changing. And that just means that there's no velocity. And so for part B, I just have a flat line at 0. Okay, now all graphs, when you actually try and make them with real objects, they curve all the time. So this next part's going to be a little strange. We go from a flat straight line to a straight line that's pointed diagonally up. And so we get a little bit of a jump. This is a constant slope, which means I have to jump to a constant value of velocity. So that's C is going to be a small positive velocity. It can be a larger one, but it has to be a positive velocity. And because this is a straight line, this also has to be a straight line. Part D is kind of has the most variety, and the line starts to curve down. So when the line curves, we can like always pick up where we left off. So we say this line had a positive slope, and what happens to it is it transitions from a positive slope to a slope of 0 and then into a negative slope. And so my graph has to cross the x-axis and end up in the negative segment. Now, if I actually gave you numbers, you would have a more clearly defined shape to this graph, but this gets the general idea. Decelerates down to 0, sits there for a segment, jumps up to a positive velocity, and then reverses direction gradually, and that's our graph. For the next part, we go to acceleration, and that's like a little bit easier because, again, remember, it's just slope is going to tell you what to do on the acceleration graph. So real quick, negative slope. So part A has a negative acceleration. Part B, 0 slope. So part B is going to be flat, and it's going to be on 0. Now, for part C, you can be a little bit creative. The truth of the matter is it's a little bit more complicated than this, but because it's constant velocity again, you can just continue that flat line. The truth of the matter is to go from 0 to some positive velocity requires some amount of acceleration. So maybe you put like a little spike in the graph that shows, well, we had an acceleration, but then that went back to 0 because we reached constant velocity. And then to travel down this negative slope, we go back into the negative for part D, and so that's what that looks like. So that's your second example. Hopefully I've given you a bunch of different looks at motion graph translating, and we will continue doing that in class.